everyone. This is the fourth lecture in the CMOS RF integrated circuits. We are now in the middle of the second module. This module is about passive RLC networks, and we have been discussing Q, or rather quality factor, as it is often called. All right. Now, we go back and the definition of Q was basically Q is defined at a given frequency. So, at a given frequency, at the frequency omega, Q is defined to be omega times the energy the peak energy that is stored in the circuit divided by the average power dissipated by the circuit. Now, notice the dimensions. Omega has dimensions of 1 by seconds, peak energy is joules. So, the numerator is joules per second, denominator is average power, power is watts, which is also joules per second. So, overall the quantity is dimensionless. So, the quality factor is a factor, dimensionless quantity. Okay. So, this is the definition of my quality factor, and then we had briefly analyzed two circuits, the series and the parallel RLC networks. So, we first looked at the parallel RLC network. I pushed in a current of I and I observed the voltage that was seen across the resistor, and here we found out that the peak energy that you stored divided by the average power that was dissipated times the frequency was given by at the resonant frequency. Resonant frequency is of course square root of L by C. So, this was Q. Okay. And then we also briefly looked at the series RLC network, where I applied a voltage source and here we observed that the Q at the resonant frequency was I think I am making a mistake. I wrote the exact opposite of what it should have been, right. Okay. So, I am sorry, for the parallel RLC network, R is in the numerator. So, as the resistance increases, when the resistance is infinitely large, you have infinitely large quality factor. And for the series RLC network, the resistance is in the denominator. When the resistance is 0, the design is lossless. In that case, the quality factor is infinitely large. So, this is our result from the previous lecture, and this is as far as we did. We also observed that at resonance, the current going through the resistor is I, and the current going through the inductors and the capacitors, one was j times q I, the other was minus j times q I, etcetera. I do not remember which is which. And similarly, as far as the series RLC network goes, the voltage across the resistor at resonance was V, and at resonance the voltage across the inductor was minus j q V, and the voltage across the capacitor was plus j q V, something of this fashion. Something of this fashion, not exactly sure of which is plus, which is minus, but does not matter, it is irrelevant. What is important to observe over here is that you can have a voltage source of 1 millivolt, and because your Q is 100, okay. And then we also briefly looked at the series RLC network, where I applied a voltage source and here we observed that the Q at the resonant frequency was I think I am making a mistake. I wrote the exact opposite of what it should have been, right. Okay. So, I am sorry, for the parallel RLC network, R is in the numerator. So, as the resistance increases, when the resistance is infinitely large, you have infinitely large quality factor. And for the series RLC network, the resistance is in the denominator. When the resistance is 0, the design is lossless. In that case, the quality factor is infinitely large. So, this is our result from the previous lecture, and this is as far as we did. We also observed that at resonance, the current going through the resistor is I, and the current going through the inductors and the capacitors, one was j times q I, the other was minus j times q I, etcetera. I do not remember which is which. And similarly, as far as the series RLC network goes, the voltage across the resistor at resonance was V, and at resonance the voltage across the inductor was minus j q V, and the voltage across the capacitor was plus j q V, something of this fashion. No. something of this fashion. Not exactly sure of which is plus, which is minus, but does not matter, it is irrelevant. What is important to observe over here is that you can have a voltage source of 1 millivolt, and because your Q is 100, you can have 100 millivolts across the inductor and across the capacitor, or you could have 1 ampere as the current source, and because your Q is 100, you could have 100 amperes rushing through the inductor and the capacitor. So, it is definitely something unexpected. All right. So, this was our first observation. Let us now look at bandwidth of such a circuit. Let us look at the parallel RLC network, and there V was equal to the voltage developed, the potential developed across RL and C in parallel was I times 1 by R plus j omega C plus 1 by j omega L, which is also equal to I times j omega L R divided by R plus j omega L minus omega squared R C, omega squared L C, I am sorry, L C R. All right. So, this is what we had in the previous class. Now, if I ask you what is the bandwidth, so I can plot V by I as a function of frequency, and at low frequencies at DC V by I is going to be 0 because omega is 0. At extremely high frequencies I have omega squared in the denominator. So, therefore, V by I is again going to be asymptotically equal to 0, and at omega squared equals to 1 by L C, this factor is going to cancel out. This factor is going to cancel out at omega squared equal to 1 by L C, which means that V by I is just going to be equal to R. So, my curve looks something like this, where this point is 1 by square root of L C. Let us not plot in terms of f, let us plot in terms of omega. Okay. And this value is equal to R, which is fine. Now, my question to you is, what is the bandwidth So, I understand that I have a band pass characteristics centered around the frequency 1 by square root of L C, but what exactly is the bandwidth of this band pass characteristics? So, normally when we talk about bandwidth, we say that at what frequency is the response 3 dB below the maximum. Or a factor of 1 by square root of 2, 3 dB is 1 by square root of 2 times the maximum. So, this is the question, and what one can derive is as follows. You can show, you probably have already done this in your control theory or in your earlier circuits classes. So, we won't do it, we won't spend too much time. So, one can show that this bandwidth, let us say this is omega 1 and this is omega 2, you can show that omega 2 minus omega 1 is going to be equal to 1 by q times omega naught. So, omega naught is 1 by square root of LC, q is whatever q you have for that particular parallel network. If it is a series network, the same relationship holds without any further modifications. There you just replace the value, put the appropriate value of the quality factor over there. You can also show that omega naught is the geometric mean of omega 2 and omega 1. So, all of this comes from your circuit theory. So, you have two equations, two unknowns, and you can compute what are the values of omega 2 and omega 1. All right. So, this is bandwidth. What does this mean for us? This means that as I increase Q, the response of my circuit becomes sharper and sharper around the resonant frequency. So, if I have a Q of 100 at a frequency of 1 gigahertz, then that means, so if this is 1 megahertz, 1 gigahertz, if my Q is 100, then the bandwidth is going to be 10 megahertz. All right. If I say that my channel, the channel spacing between two subsequent channels is 100 kilohertz. GSM has a channel spacing of 100 kilohertz, or is it 200 kilohertz? All right, 200 kilohertz. And you want to listen to what is going on in your channel, not in someone else's channel. The center frequency is let us say 800 megahertz. All right. So, if you want to design, if you are asked to design a band pass filter, or if you are asked to design a circuit that can zoom into 200 that can resolve 200 kilohertz channel spacing at a center frequency of 800 megahertz, then what is the quality factor that you need? You need a quality factor of 4000. Now, such kind of quality factors are very hard, if not impossible to achieve. All right, even with discrete components, a quality factor of 4000 is most probably not going to be possible to achieve. On an IC, on an integrated circuit, you can achieve quality factors probably up to 10. Okay. So, anyone talks to you about designing a circuit which has Q of more than 10, you stay away, or you accept it as a big challenge. All right. Okay. I mean, first of all, Q is proportional to frequency. So, maybe at higher frequencies you can achieve better Qs, better quality factors, but even then a Q of 10, Q of 15 is probably the most you can achieve on an integrated circuit. Okay. If you use discrete components besides integrated besides the integrated circuit, if you also are allowed to use discrete components, you know, your inductor and capacitor, these are, let us say these are discrete components, not on an IC, then maybe you can achieve a Q up to 100. Okay. These are reasonable numbers, more than this becomes unreasonable. So, that kind of tells you that if someone asks you to design a band pass filter for GSM which has a 200 kilohertz channel spacing and you have to resolve this channel spacing in the band pass filter, then he should be told that it is unreasonable for him to expect such a filter out of you, because the Q of such a filter would be 4000. It is not possible to do this. Okay. Obviously, people do it even then, right. I mean, you do resolve 200 kilohertz channel spacing. So, there are other techniques to do it. You translate it to baseband where the center frequency is much lower. Okay. So, you use a mixer. So, this is what we do. So, instead of trying to resolve 200 kilohertz channel spacing at 800 megahertz, we mix the frequency down. Let us say I bring the frequency down, I mix it with 799 megahertz. Okay. Then the new center frequency becomes at 1 megahertz, and at 1 megahertz it is very easy to resolve a channel spacing of 200 kilohertz, because all I need is a Q of 5. Okay. So, this is typically what we do. We do not try to build this super filter at RF frequencies. Okay. The next observation that is important is the transient response. So, if this is my network and instead of a continuous current, suppose I apply a pulse or a square wave or a step function. Okay. Then one can show, it is not very difficult. Okay. If it was only R and C and you apply a step function, then what is the voltage going to look like? The voltage is going to look like a going to have a time constant, RC time constant. Yes? Is this okay? So, this is what is going to happen if it was just an RC, and now we have what is this value going to be? Now, on top of it we also have an inductor. So, what do you expect? You expect ringing. And if the resistance is more, then this shoots to a larger value, and the ringing is also going to continue for a longer duration. Okay. Also, if the resistance is more, then the Q of the network becomes more. If the resistance had not been there, then you would basically see a perpetual sinusoid oscillation as a response. Now, there is resistance. So, as a result it is going to be a damped oscillation. The more this, the less this resistance is, the more the damping is going to be. typically if you observe this waveform on an oscilloscope, you can just look at it and estimate the Q of your circuit. So, all you have to do is count the number of cycles you can see. So, over here I have drawn 1, 2, 3, 4, 5, 6 crests and troughs. So, I can estimate, and off the back of my head I can say that most probably this network has a quality factor of 6. All right. So, this is observation number 2. This also can be shown, this also can be proved without great difficulty. I am not going to prove it. You can take a look at the books, and it is not very, it is quite an easy derivation. All right. So, you can look at the frequency response and estimate Q. You can look at the time domain response and estimate Q of the network without any great difficulty. This holds both for series RLC networks, parallel RLC networks, anything. I mean, I have shown it only in case of the parallel RLC network. In fact, I have not done any proofs whatsoever, but you can do it for any configuration. Now, the next important thing is a series to parallel transformation. Now, the question is that suppose I have a series RLC network. Is it possible to transform this into an equivalent parallel RLC network? Is it possible to do this? So, point blank the answer is no. Why not? Why not? Why is this not possible? I mean, I said no. Why not? Well, let us just look at 0 frequency. At 0 frequency, the series network looks like an infinite input impedance. Let us look at the input impedance. At DC, it is infinitely large because the capacitor is open circuit. At high frequencies, it is infinitely large because now the inductor is an open circuit. And then look at the other one. At DC, the input impedance is 0 because the inductance is a short circuit. At high frequencies, the input impedance is 0 because the capacitance is a short circuit. At the resonant frequency, the input impedance is R in this case and R in the other case. Okay. So, the only semblance of similarity is at the resonant frequency. So, if I want to create a series RLC network that mimics a parallel RLC network, then point blank the answer is that it is not possible. However, if I want to create a series RLC network that mimics a parallel RLC network at resonance, it is possible to make such a thing. It is definitely possible to make a series RLC network that mimics a parallel RLC network at resonance or at any other given frequency. So, if you specify one frequency point and say that I want these two networks to be identical at this one frequency point, it is possible to arrange for that to happen, not otherwise. You can't do it over the entire frequency range. All right. Now, let us try to go step by step. So, first observation is, if you want to do a series to parallel transformation or a parallel to series transformation, then it is in general not possible to do such a thing. Second observation is that it is possible to do such a thing at some frequency point or points. All right. So, given this information, I would like to transform a series LR network to a parallel LR network. Okay, this is what I would like to do. I would like to transform back and forth between a series LR network and a parallel LR network. First of all, I want to know if this is possible at some frequency, it should be possible, and how are the two networks interrelated. First observation is, it is definitely not possible to transform this over entire frequency range. A series network can never mimic a parallel network. This is first observation. Okay. So, we have to choose a frequency of interest. Let us pick a frequency of interest omega 0. Okay. Omega 0 so happens to be the resonant frequency of LP with CP, which is not yet there. Okay. So, it is not yet there in the circuit, but I am going to choose omega 0 to be the resonant frequency of LP and CP. Okay. Now, given that information, what is the Q, the quality factor of my parallel RLC network? Remember, the parallel RLC network, if R increases, then if R tends to infinity, then the resistance is an open circuit, then it should have infinite Q. So, if R increases, my Q should increase. So, that is how I remember what is what. Okay. This is the result for my parallel RLC network, and I really do not want to involve CP in this. So, what you can recall is that LP times CP is 1 by omega 0 squared. So, Cp is really 1 by Lp times omega 0 squared. So, this is something that you can recall. So, you plug in this. Fine. So, this is the quality factor of my network. Okay. Now, with this in mind, what is the input impedance that I see? Let us not think about Cp, Cp is there outside, like I have drawn in the other case. Omega 0 is the frequency of interest, where I want to make sure that the two networks are identical. So, this is the input resistance, input impedance. Now, if I want to find out the real and imaginary parts of this, I have to multiply the numerator by the complex conjugate of the denominator, and so this is what I have got. Now, notice that Q is equal to R by omega 0 L p from my earlier R p. Okay, this is R p. I am sorry. Yeah. So, therefore, Q squared is equal to R p squared by omega 0 squared L p squared, and 1 plus Q squared is this plus 1, which happens to be equal to omega 0 squared L p squared plus R p squared by omega 0 squared L p squared, right. It is wonderful. 1 by 1 plus Q squared is exactly what we want. The denominator matches up. The denominator matches up with what I need. So, this quantity is equal to R p times 1 by 1 plus Q squared plus j times omega 0 L p R p squared divided by omega 0 squared L p squared times 1 by 1 plus q squared, right, which is equal to R p by 1 plus q squared plus j times R p by omega 0 L p whole squared by 1 plus q squared, which happens to be equal to q squared. Okay. So, this is no, this can't be right. How is this correct? Is this correct now? Yeah. Okay. So, do cross check every result, every step, do cross check by yourself to see that it is dimensionally consistent. Dimensions are very important, especially when you are doing lot of mathematical jugglery. I mean, whenever you are doing manipulations, make sure dimensions of each and every term are the same and what you expect them to be. This is usually a very handy sanity check. So, I could correct myself just based on dimensions, right. All right. So, this is Z in of the parallel network. Now, Z in of the series network is very easy to know. At the frequency omega 0, that is my frequency of interest. This is the Z in of the series network, and these two input impedances have to be equal to each other. That is when I can transform the series network, the parallel network to a series network and vice versa. So, therefore, R s has to be equal to R p by 1 plus q squared, the real part has to be equal to the real part, and L s has to be equal to L p times q squared by 1 plus q squared. Okay, what does this mean for us? This means two things. Point number 1, let us look at, let us think about large quality factors. Let us say my q is 100, or let us even say my q is 5. If q is 5, then the series inductance L s is equal to L p times 25 by 26, which is almost equal to 1. So, L s is almost equal to L p when q is 5. Okay. What happens to the resistor is something very dramatic. The resistance value has to drop dramatically by a factor of q squared. 1 plus q squared is almost equal to q squared, right. So, let us go back to what I wanted to do. I wanted to transform a parallel LR combination to a series LR combination. And what I found was that the series resistance has to drop by a factor of 1 plus q squared. The series inductance is more or less almost equal to the parallel inductance. So, there is no great change in the value of the inductance per se. The change is in terms of the value of resistance. When you transform it to series, it has to drop dramatically. Now, can we do a reverse transformation? Of course, we can do a reverse transformation. And oh, just by the way, what is the Q of the series RLC network now? So, if I have RL in series, there is also C probably in series with that. I do not care about that. We are transforming R and L into a parallel combination. So, when we do this, the Q is inversely proportional to the resistance, right. Okay. So, the Q is inversely proportional to the resistance, and what do we have here? So, the new Q of the network is also now going to be something else, okay, if we are talking about a series RLC network now. Right. So, the Q has changed. This was my old Q. No. Okay. Do you agree with this? So, Q of the new series network is going to be equal to the old Q. So, either way it works. Now, that means that if I am going to transform the series network into a parallel network, then I can just do the same thing. So, suppose I have RS and LS and I want to transform it to a parallel network with RP and LP, then I just have to do the precise opposite, which means that RP now has to be much larger than RS and LP has to be equal to more or less the same as LS. Okay. And this Q is the original Q that we started from. Is this okay? So far so good. So, we can do back and forth between series RL networks and parallel RL networks at a chosen frequency of interest. And all this is possible by assuming that you have the required capacitor in parallel with it, and then you do the Q computation in your head. Okay. Presumably, if you can do this for if you can do a transformation between series RL and parallel RL networks, then you should also be able to do a transformation between series RC and parallel RC networks. And here the inductance is imaginary. Okay. The inductance is imaginary. So, we will equate the input impedance looking in from these two terminals, real and imaginary parts of these, and we will figure out how the resistor and the capacitor need to be numerically related to each other. So, how are we going to do this? Same procedure. First of all, we have the observation that Q of the parallel network is equal to, is proportional to Rp by square root of L by C, and I do not want to really use L over here. So, let me try to get rid of L. Okay. So, Q is Rp times omega naught times Cp, that is the quality factor of my parallel R and C combination. So, Z in is equal to 1 by Rp plus j omega naught Cp. This is at the frequency of interest omega naught, and this can be further simplified to Rp by 1 plus j omega naught Cp Rp. However, we need to convert this to real and imaginary. So, we have to multiply by the complex conjugate of the denominator. Okay. And final result is this is my final result, and what is very neat over here is the fact that Q is equal to omega naught. So, this is Q squared. okay, and q squared by 1 plus q squared okay. So, something like this. So, this is my input impedance of the parallel network. Input impedance of the series network is easy to figure out. And that kind of tells you what is going to be what. So, therefore, R s has to be equal to R p by 1 plus q squared, and C s has to be equal to C p into 1 plus q squared by q squared. So, that is the only difference between the earlier result. From the earlier result, this is the only difference. So, earlier with the inductor, q squared was in the numerator, 1 plus q squared was in the denominator in this part. Okay. So, this is the only difference. Otherwise, it is the same thing. If I have a large resistance in the parallel network, then for the series to have the equal amount of q, I need 1 plus q squared times less resistance in series. The capacitance value does not change much when q is large. So, if I have a q of 5, let us say, then the capacitance value is going to remain more or less the same, just a little bit more than the original value. You can also do the parallel to the series to parallel transformation. R p is going to be equal to R s times 1 plus q squared, and C p is going to be equal to C s times q squared by 1 plus q squared. Okay. So, this is also going to follow. The q of the network is going to remain unchanged between the series and parallel transformations. So, just like before, the q of the series network was so earlier the q of the series network was this much, the q of the parallel network was q itself was the q of the parallel network, and we showed that the q of the series network also remains to be equal to q. Now, in this case you will get the same exact result. The q of the network will remain unchanged over a series to parallel transformation or a parallel to series transformation. What is important over here is that these transformations can be done at one frequency of interest, that is omega naught. Omega naught can be anything, because the inductor can be chosen to be anything. The inductor is imaginary, remember, or the capacitor in the earlier case was imaginary. This capacitor over here is something that I imagined, right. Depending on what omega naught I want to do this transformation at, I choose this capacitor in my head and place it in my head. Okay. I imagine this the presence of this capacitor, and then I do the transformation, and then everything falls into place. The capacitor is useful only to visualize what q is going to be. the capacitor is useful only to do the appropriate, to use the appropriate formulae, otherwise the capacitor is meaningless. As far as this derivation goes, equating Z in parallel to Z in series, I have not used the capacitor at all. The presence of the capacitor is useful only for the Q, the definition of the Q. Okay. So, with this I will summarize what we have done today. So, to start with, we talked about bandwidth. What is the relationship between the quality factor and the bandwidth of a circuit, and you can go back to your network theory and it can be proved that the bandwidth is going to be the center frequency divided by the quality factor. So, that is number 1. Number 2 is we talked about the transient response. In the transient response, the number of times the circuit rings gives you an estimate, a rough estimate of what the quality factor of the circuit is. I have not proved this, but you can look at the books, you can look at Thomas Lee's book, which is a very good reference for this course, and the derivation is done there. After that, we talked about series to parallel transformations. First of all, it is obvious that a series to parallel transformation is meaningless when we want it to work over all frequency range, over the entire frequency range. A series to parallel transformation can work at a specific frequency. So, given that we are interested only at a specific frequency, can we transform a series LR network to a parallel LR network? We can, and the way it works is that the parallel LR network should have 1 plus q squared times the resistance of the series LR network. As far as the inductance itself goes, the inductance itself is unchanged, more or less unchanged. We can also transform a series RC network to a parallel RC network and vice versa. Once again, the capacitance value itself remains more or less unchanged. The value of the resistance in the series RC network has to be 1 plus q square times lesser than the value of the resistance in the parallel RC network. So, this is what we have covered today. Thank you.